In this video, we're going to talk about Hess's Law. And what Hess's Law states is that when a reaction is the sum of two or more component reaction, then the net change in enthalpy is going to equal the sum of the change in enthalpies for each of the component reactions. So let me show you what I mean. If we look at these two processes, you can see that they would add up to this overall process. How can we see that? Well, when you're adding up equations, anything that appears on opposite sides of the reaction will cancel out. In this case, we can see that H2O as a gas appears on both sides, so we can simply eliminate it once we add these up. And the net equation that we end up with excludes that water as a gas, but it contains everything that's remaining from these equations. And because when we add these two equations, they give us this net reaction, we can also add their enthalpy changes to give us the enthalpy change of this reaction. So this is useful when we know the energy changes associated with some reactions, and we can combine them in a way that we could figure out the enthalpy change of something else. So applying this, there's two things you can do. This one was pretty straightforward because they just simply add up. But sometimes you're going to need to manipulate the equation, and you can do one of two things. You can either flip the equation, meaning convert the products to reactants and vice versa. And when you do that, since it's essentially reversing the process, you're going to also reverse the sign for delta H. The other thing you can do is multiply the whole equation by a coefficient. And when you do that, say you were multiplying everything by a coefficient of 2, that means the reaction would essentially be happening twice, and you'd have to double the enthalpy change for the system as well. So let's apply these rules, or these tactics, to this reaction. So let's say we're given these two reactions, and we know the energy changes for both of them. And we have to try and rearrange them in a way that they add up to this net equation. These components will add up to this net equation of nitrogen gas and oxygen gas combining to make NO. So when we look at this, we try and figure out where things are and look at the coefficients and see if we can manipulate these to get there. So I see that NO is a product. So I look up here, I see that it's also a product. So I don't need to flip the equation. But I do see that this only has a coefficient of 2, where that has a coefficient of 4. So the way that I can amend that is I can multiply this by 1/2, and that would give me the equation. It would make it 2 ammonia plus 2.5 oxygen gives you 2 nitrogen monoxides and 3 waters. So I just multiplied everything in there by 1/2, and I also did that to my delta H. Then I look at the next equation, and I go, all right, I see that nitrogen is a reactant, and it's a product in this one. So in my head, I got to think, I need to get that over there. The only way I can do that is by flipping the equation, converting my products to reactants and my reactants to products. But I also see that I only have one N2. So just like in the problem before, I'm going to multiply it by 1/2 so I can get it to have the right coefficient. Now, you might be thinking, yeah, but what about oxygen? Well, the thing about oxygen in this case is that it appears in both of these. So why don't we look at the ones that only appear once in each case and see if the oxygen shakes itself out? Hopefully it does. So now I have my two equations manipulated. Let's see if they add up to my net overall reaction that I'm looking for. So, things that go away that appear on both sides. I have 3 waters on each side, so those cancel out. I also have 2 ammonias on each side. Those cancel out. And while the oxygen doesn't completely cancel out, when you take 1.5 away from 2.5, you're left with 1. So this gives me a net reaction of N2 plus O2 gives you 2NO, and the delta H will be the sum of those, which is positive 180 kilojoules.